Hi, my name is Arlene Olivero, and I'm a spatial ecologist with the Nature Conservancy's Center for Resilient Conservation Science. I worked on the freshwater resilience analysis, and in today's video segment, I'm going to show you how to explore the potential water availability component of the water score using the Resilient River Explorer. We'll start by going to the Explore the Data tab. This tab helps users better understand a watershed's freshwater resilience score. You can explore the metrics and source datasets used to assess each resilience component. But first, let's click on the component metric diagram here to see how potential water availability fits in the overall model of resilience. We can scroll down and see that potential water availability combined with the current flow alteration comprise the water score. Green boxes indicate the metrics used to assess potential water availability, while the red font tells us the source datasets available for viewing in the tool. Now let's click on potential water availability in the left panel. You'll see the map shows the potential water availability results now. Watersheds in blue are expected to have higher potential water availability into the future due to their natural or enduring setting. The potential water score accounts for the presence of surface water, topographic storage, and includes adjustments for groundwater availability. We reasoned that areas with greater natural capacity to store water and areas with greater enduring groundwater availability would be more resilient to climate change, particularly as precipitation patterns change. When looking at this map, it's important to note that this metric was scored within two major zones of the US, an arid western zone and a humid eastern climatic zone, which splits the US at about the 100th meridian, about right here. So the browns you see in the Appalachian Mountains here should be considered to have lower enduring potential water storage and availability within the humid climatic zone, while the browns you see in the desert Southwest here have lower enduring potential water availability within the arid climatic zone, but these browns are not meant to be directly compared to each other. It's also important to remember that the influence of potential water availability on the overall water score varied by major climatic region. So the potential water availability had a larger influence on the final water score in the arid zone, where available water was a highly limiting factor, while flow alteration had a larger influence on the water score in the humid east, where available water was a less limiting factor overall. We can turn on the final water score to see the effect of that integration weighting. For example, many watersheds in the Appalachian Mountain area actually scored blue and above average in the final water score, given their current intact flow regime was weighted more highly in the integration. So again, even though they had low natural enduring water storage and availability, they scored very high for intact current flow regime, which was a metric that focused on current dam storage, water withdrawal, and impervious surface impacts in those watersheds. But let's go back to potential water availability. And I'd like to zoom in on an area and explore the score and the input data in more detail. So I'd like to explore the area around Flagstaff, Arizona, near the Grand Canyon with you. So I will scroll down a little here. And within the map layers, I'm going to turn on the states. And that will help us zoom to the Flagstaff, Arizona area. You can see Flagstaff here. I'll zoom in a little further. And I see quite a bit of variation in potential water availability for this area. Much of the area has lower enduring potential water availability in the browns, but I also see some areas scoring average and a few areas scoring above average. So let's turn on the additional metrics and the source data so that we can explore the inputs and better understand why these areas scored as they did. So we can now expand this potential water availability box, and we have more options here of data to explore. Let's start by going within the surface water section here to review the surface water topographic storage index. So I'll turn that on. And we'll click this info button here. And we can learn again that surface areas that store or have perennial surface water support freshwater resilience by providing direct habitat for freshwater biota and by storing precipitation and providing more gradual release and continual access to water throughout the season and during droughts. So to estimate the natural storage capacity, we developed a 30-meter topographic grid where features were weighted based on their water presence and water storing capacity. So this included things like confirmed wetlands, perennial streams and rivers, topographic depressional landforms such as floodplains, and moisture accumulating depressions and flats. And it also included high elevation areas modeled to have more persistent snowpack in the western US, given their high elevation and aspect. So I'm going to change the transparency here a little bit so we can see a little more of the underlying base map labels and topography here. And I'd like us to zoom in on this area, San Francisco Peaks. I'm going to zoom in on this area a little bit. So we can see that most of this mountainous area here is scoring low in its topographic storage index. And again, this area has very steep slopes that cause water to run off quickly, given there's not a lot of depressions here to store water when it rains. And so that accounts for most of the low score of this area in general that has a lot of mountains and very steep slopes and not a lot of depressional storage areas. But there is one watershed here that's getting a high score. So I want to look at that a little bit more closely. And I see that it's right at the top of this mountain peak. So it's actually at the very highest elevation. And I also noticed that it has a northern aspect. And so it would get less solar radiation. And so it likely got points for modeled persistent snowpack in that area, a very high elevation northern aspect. And again, that snowpack would provide a source of water throughout the summer as the snowpack gradually melts. That probably explains this particular watershed's high score. But what might explain these watersheds' high score? They're at a lower elevation. To explore that, I suggest we go down here and turn on the NWI wetlands. And when I turn on the wetlands, I now see that this watershed here has a large emergent wetland and a lake. So again, those features would increase the surface water topographic storage index. And I also see this watershed over here has also large amount of emergent wetland. Again, this kind of depressional areas that would store water, confirmed wetlands, those features increase the score. So now I'm going to turn off the NWI wetlands, and let's look at the next input layer here, high spring density. So the map now shows watersheds in green that received an increase in their potential water availability score due to high density of springs and seeps. And again, these springs are indicating movement of the groundwater to the surface. To see the exact spring locations, we can turn on this button here. And again, we can notice in this area where the springs are located and the watersheds that had a particularly high density of springs and received an increase to their overall potential water availability score. Now let's turn off the springs and seeps and turn on the next data set here, high perennial stream and river density. If I turn on this particular metric, I see again some green watersheds that received an increase to their overall potential water availability score due to having high density of perennial streams and rivers. We can expand this box and turn on the flow regime data to see exactly where those perennial and intermittent streams and rivers are located. So again, you can see the watersheds in green have some of these perennial stream and river features, which are particularly important in the arid zone, again, as they're places where water is reliably found throughout the year. I'm going to turn this off. And now let's look at the last input data set, groundwater depletion. Here we see pink watersheds that received a decrease in their water availability score due to groundwater depletion, likely from climate change or groundwater withdrawals or both factors. This factor was used in the arid zone. And again, we can further dig into this metric by expanding this box and reviewing two of the input data sets used. So I'm going to turn off this resilience result so we can focus on reviewing this first input, the GRACE data analysis. So the GRACE data analysis of groundwater depletion was an assessment based on the alteration of shallow groundwater levels from 2003 to 2021, so kind of the current period, compared to the historic levels of groundwater from 1948 through 2012. So the penalty for groundwater depletion in our analysis was only applied in the arid HUCs that had the most highly altered groundwater class. So this 0 to 20% red group of input area. Again, those areas are where the shallow groundwater was most frequently at 0 to 20% of its historic level, so highly altered. The depletion penalty was then adjusted based on a watershed's hydrologic landscape geologic setting, which you can turn on with this other toggle here. The geologic hydrologic landscape setting map highlights areas that, based on their geology, would have higher potential groundwater, such as areas of limestone. A larger groundwater depletion penalty was applied in regions with the greatest reliance on groundwater, as indicated by their geologic groundwater potential. So the red high depletion pixels we saw in this previous map here, the red pixels that fall on top of the blue, the highest groundwater potential given their geologic setting, those areas would get the highest penalty, while the red area of high groundwater depletion that fell within this more moderate groundwater potential due to the geologic setting, that area would get a slightly lower or less penalty. With that, we've covered the inputs to the potential water availability. And for more information, I would encourage you to download the report and read the entire chapter about the water score and the potential water availability, the flow alteration, and other information about how we developed the overall resilience score. So to get the report, you can go to more information. You'll find the report link here, along with other links that you can use to provide feedback, download the data, or access some of our other webinars and video resources. So I hope that this tutorial helped you understand the potential water availability component of our water score. And thank you for your interest and attention.